Howdy. From Lab 7, we will start to design the single cycle processor. And in Lab 7 and in Lab 8, we will design some modules of the single cycle processor. And in Lab 7, we will design the science standard and ARU. And for the science standard, I think you already learned in the class. So I just take a example. If we want to extend a 16-bit address to 32-bit address, we need to just decide. We need to know if the address is positive or negative at first. So if the leftmost bit, the 15th bit, if it is 1, it means it is negative. We just extend 16 leading ones and make it also negative. If the uh, leftmost bit is 0, means it is positive. We just extend all leading zeros, make it still positive. So for our science standard, we the input should be 0 to 25th base of the instruction base. It is a 26-bit address and a 2-bit control signal. Actually, we can check the textbook green sheet and for the core instruction formats. Uh, we can see that we need to implement D tab, I tab, B tab, and CB tab. And for the first several bits is the opcode, and we don't want to extend that. So for the effective base, and for the B tab, it is the longest for the BR address. It is from 0 to 25. So we just take the last 26 bits as our input. Even though maybe for the I tab and D tab, the effective address is not that long enough, but we need to take the longest one as our input. So because we need to extend 4 tabs, so for the control signal, 2-bit, maximum of 4. So we can use the control signal to select which type of the instruction we want to extend. And for the for the science standard, we just want to extend the effective address. So for the D tab, we just want to extend the DT address from the 12 bits to the 20 bits. For the D tab, it's from 0 to 25, the BR address. And for CB tab, it is from 5 to 23, the conditional branch address. And for the I tab, it is ARU immediate. I have listed how to extend these 4 tabs to a 64 bits of address. And you can just compare with what I just explained. We need to extend the effective address, and with this, with all these format, the extended bits, and see just how we extend that. But just a quick reminder, this is not the code format. So you need to just write the code based on these values and make it can be compiled correctly. Okay, and for Lab 7, we also need to write your own test bench to test it. And for the how to write the test bench in Lab 6, we already provide some example test bench. So you can just learn how to write the test bench from this. Okay, maybe for for the science standard, it's a little complicated, and you need to write your own test bench. Yeah, but we only have 2 modules to design, so I think it's okay. And for question 2, it is we need to design an ARU, and we need to use the ARU to support at least AND, OR, add, sub, and pass B instruction operations. And you must remember that each operation should have a delay of 20, and we need to use the non-blocking assignment in the always block. So we need to use the behavior model. Yeah, behavior style Verilog. So for this operation, actually for the AND OR add sub, it is easy to implement. Just use the symbol. And for the pass B, actually just the output equals to bus B. So just pass the B input, which is bus B. And the input should be all 64 bits for bus A and bus B. And we also have a 4 bits ARU control signal. It is 4 bits, so it at the maximum it can just select 16, support up to 16 functions. But here, at least we just implement these 5 operations. And if you can extend it for your own purpose, and I think you can find more functions on the textbook and their corresponding area control. For the output, it is bus W, also 64 bits, and we also have a 0, which is a Boolean variable, means which means it's only 1 bit. And when the bus W is 0, it is 1. And else it will be 0. And we have the test bench for that. And we also have the sample code for that. For this area, it provides the code structure. So you can just implement these 5 functions inside the code structure. Okay, I think that is all for Lab 7. Yeah, thank you.